I start recording. All right. So today you're going to, my plan is to start talking about families of discrete distributions, discrete random variables. And hopefully we're going to get all the way to the end. If not, we are going to spend our 1 hour lecture on Tuesday to finish this chapter 3. So also today I'm going to finish early in the second hour, so I'm going to give a single block lecture of 1.5 hours. Okay, by the way, this is not an April Fool's Day joke, so this is real. I have to leave early, so today is April 1st, but yeah, something different than our regular classes. It's not because it's April 1st. I have some errands to attend to at 11:15, so I'll have to leave early. So I'm going to have a single block lecture of 1.5 hours, so we're not going to have a break. But you're free to leave and come back anytime you want. All right. So last time we were at, you will have quiz today also at 6 p.m. The regular weekly quiz. It's going to be about. It's not going to be about what we have seen. We are going to see today. It's what we have seen earlier about discrete random variables, their joint distributions, computing expected value and variance. It will be, and again, a quiz that will take 1 day. We will give you 1 day to work on it. It's a really simple question, really, but it will help you to exercise on what we have learned. Okay, computing the, I think, no, it's not joint probability. I think if I remember the question correctly, it's going to be about a single random variable computing its expected value and variance. All right, so. But it will be a discrete variable. All right. So we talked about, we didn't finish the entire set of slides last time. We talked about how to compute the expected value, how to compute the variance. Variance is the expected value of the squared difference between the random variables and their mean. Because if we didn't get the square, the result will always be 0 because of linearity of expectation. And at the end, when we solve this, we get this formula. And this formula actually tells me that, remember, we solved an example last time, which was about the variance of number of heads in 3 coin tosses. And I was worried that, maybe in this case, I hope the variance is not the same as mean squared. Actually, it will only be, if you look at this, if you look at the variance, the mean squared, if it's equal to the, we were computing the squared expected value of the number of heads, which turned out to be like 3, right? It wasn't 2.25, which is the square of the mean value. I'm referring to our Tuesday's class. So we were computing this. I was saying that this is not a linear function, so this is not necessarily equal to mu square. If it was equal to mu square, it means that the variance is 0. So it's only going to be equal to the expected value of x squared will be equal to mu squared only if the variance of that discrete variable is 0. So I should have known that when I gave that example, because we have the variance is not 0. Variance 0 means that all the discrete random variable gets a single value. There is no, all the values are exactly at the mean. So if a random variable gets different values, its variance always going to be non-zero. Zero variance means that everybody get the same grade. For example, every time you perform an experiment, you get the same thing. There's no randomness about it. That's when the variance is going to be equal to 0. And as you can see, the variance 0 means that these two are equal to each other. So if the variance is non-zero, this expected value of x squared is always going to be something different than mu squared. This is just a side note of what we have done last time. And this is like the squared distance between our random variables and the mean value. That's the expected value of the squared this I mean, actually, yeah, it's this exactly square distance between these two things. And if you want to get your units exactly the same as your random variable, if you want to get like the average distance between your random variables from their means, how the random variables change differ from the expected value, the center of that distribution, you use standard deviation, which is the square root of variance. So this is for a single random variable. Let me also change my mouse pointer size. I always forget about this, sorry. Okay, now, yeah, it's better. And then we are going to talk about, I told you that you may do this as an exercise. So two fair dice are tossed. What is the expected value of the random variable x when x is the sum of two dice? And what is the variance? So there are different ways you can solve this problem, where you can use the two dice. Yeah. Also, let me check whether I'm recording. Yeah, I'm recording. The chat should be open to everyone, but I think I need to get to the main menu of this and give you. I don't have that here. I need to first stop sharing so that I can see the Cisco WebEx meeting menu. I'm going to do that. Participant assigned privileges. So yeah, it's like somehow WebEx gives this publicly chat with everyone, only the attendees who attend the meeting, like at the beginning of the meeting. I don't know. When I enter here again, the publicly with everyone is like half checked. So I need to give that privilege every time if you're if there are attendees that are coming in later. So now you should, I have given that you should be able to chat with everyone now by selecting everyone in the chat box. All right. So let me share my screen again with you. All right. All right. So you should be able to select everyone now. Right. So let's take a look at this example. How do we find the expected value of the random variable of x when x is the sum of two dice? So what we need to do is the possible values that x could get is from 2 to 12, right? There are two dice, regular dice, six-sided dice, 1 to 6, each of them. So we can get 1, 1, we can get 6, 6, so 1 and 1, 6 and 6, and the number of possible cases you're going to have, I mean, if you, the sample space is going to contain 36 different values. 36 different values. It could be 1, 1, 1, 2, 1, 3, 1, 6, and 2, 1, 2, 2. So if you list all these things, the last thing you're going to get is 6 and 6, and the total number of outcomes that you can observe is 36. So only one of those outcomes is going to give you a summation of 2, right? So it's probability. If they're all equal, if all these are equally likely, it's going to be 1 over 36. And the probability associated with this is also 1 over 36. In other words, what you're going to do is you're going to compute this summation. Actually, let me write it. So 1 over 36 times 2 plus, what is the probability that we're going to get a 3? It's either 1, 2, or 2, 1. Therefore, its probability is, I think, 2 over 36. Is there any other way to get 3? 1, 2, or 3, 1. Those are only two probabilities. So this is the probability that you get a value of 3. And you're going to do this all the way until the last one, which is 1 over 36 times 12. Okay, so the random variable's value is weighted with its probability of this probability of this random variable, to observe this random variable is this value, the probability that x is equal to 12 is equal to 1 over 36. So this summation, as you can see, is a weighted average, and it will give you the expected value of the sum of two dice when you throw them. All right, so in order to find the variance, so there's also another way. What if is it possible? The alternative is if I define two other random variables, y and z, to indicate the value of the first dice and value of the second dice. So it's going to be something like the expected value of y plus z, right? It should be like that, isn't it? I mean, if I just define the expected value of the number on the first dice, the expected value of the number on the second dice, so the summation is simply the expected value of these two things. And then, because of linearity of expectation, whether they're independent or dependent, this should be equal to expected value of y plus expected value of z, all right? Since y and z are actually the same thing, I mean, they're throwing a dice, so they will, instead of trying to compute all this thing like this, you could have computed them like this and use linearity of expectation to sum the values of the expected values of individual dice. Okay, so when we have summations, we can actually make use of linearity of expectation to solve this in a simpler way. Just compute the expected value of throwing a single die and sum it up with itself or multiply it by 2. You'll get the expected value of the sum. Okay, summations can be, since summations are linear, they can be taken out like this. But in general, if the product of the values on the dice, for example, it was yz, we wouldn't be able to do that if we don't know these two events are independent. Now we're going to come to that actually. If two events are independent, we'll be able to say, their multiplication, the expected value of their multiplication will be the multiplication of their individual values. We'll see that. But these are the two possible alternatives that you can compute. You can solve this example. And so here is another thing. So this one is about a continuous variable with a probability density function fx is equal to 1 over 2. Okay, so what kind of between values of x and 2. So what kind of a probability density function that is? Let's see. So in this example, we are given a continuous function. So this is fx, it's PDF, probability density function. And this is 0, this is 2. Okay, so it says 1 over 2. So it's a constant function like this, and all the other places it's 0. Okay, so in these parts it's 0, and it's defined like this. So does it mean that the probability to obtain 1 exactly is equal to 1 over 2? Is this the probability? So for example, if this is a continuous variable, what is the probability that x is equal to 1? Exactly. Thank you. 0. Yes. Perfect. So because this is like a trick question, because since this is a continuous variable, there are infinitely many values here. To get exactly 1 is equal to 0. So we can ask something like this: what is the probability that x is between 0.8 and 1.2, for example? In order to do that, we need to, the area under this curve from 0.8 to 1.2 is going to give me the probability. And if you look at that, since this is a very simple function, which is just a straight line, fx dx, it's just computing the area of this rectangle, right? Which is 0.4. This side is 0.4 length, and this side is 0.5 length. So that probability is 0.2. Okay, so the probability that x is between 0.8 and 1.2, so it makes sense, right? I mean, it's like 1/5 of the entire space domain of x from 0 to 2. Since it's 1/5, we expect exactly 1/5 probability in this region. So this is the probability. 0.2 is the probability to have x in this between 0.8 and 1.2. So we are asked, what is the expected value of this? So the expected value of this, I think it's like, this is the center of gravity. Intuitively, the expected value of this x here, I expect it to be 1, all right? The center of this distribution. But in order to mathematically find it, we have to do this. We have to go all the way from minus infinity to infinity to compute x fx dx. Okay, we need to compute this integral. And this fx is 1 over 2, so you have to, since it's not defined, it's only defined between 0 and 2, we have to get this definite integral from 0 to 2, 1 over 2 x dx. This is the result, this is the expected value. And again, how did I get to this? X times fx dx, since fx is equal to 1 over 2, it's equal to this one. And therefore, you need to get your integral. The integral of this thing is x squared divided by 2, right? Was it like that? So x squared divided by 2 from 0 to 2, and I'll get this 1 over 2 outside. So this is 0, this is 4 over 2. If you give 2, 4 over 2, it's going to be 2. 2 times 1 over 2, it's going to be 1. So this is how you find its expected value. In order to find variance, exactly, so it's going to be x squared over 4. This 1 over 2 goes here, the same thing. In order to find the variance, in addition to the mean, if you remember, the variance is this, the expected value of x squared minus the expected value of x squared, which is the mu, all right? So this is the formula for variance. So in order to compute variance, first you need to compute the expected value, mean itself, which is here 1, and you also need to compute the expected value of x squared. This is not variance by itself, okay? Variance is this difference. So therefore, in order to find the variance in this case, all we need to do is, again, from 0 to 2, take the integral, this time 1 over 2 fx x squared dx. Okay, so if you look at this function, this gx is x squared right now. I write x squared here. I write, now I'm going to weight these x squares again by the PDF. I don't square the PDF, okay? So the PDF always remains as it is inside this function. So this is the expected value of x squared is equal to fx x squared dx. So this is going to be x cubed divided by 6, right? So it's going to be, let me write it in a new place. X cubed divided by 6 from 0 to 2. This one is 0, so it's going to be 2 cubed, 8 divided by 6, right? Which is what? 8 divided by 6, 1.333. Yeah, it's going to be 1.3333. So this is the variance. Take the square root of this, you're going to get the standard deviation. Oh, this is not the variance, by the way. So again, I made the same mistake. This is not the variance. This is the expected value of x squared, right? The variance is this minus the expected value squared, all right? So, which is, then the variance of this is going to be 0.3333. Okay, so as soon as I found this, I treated it as a variance, but I made the same mistake that I warned you about. So this is the expected value of x squared. Variance is this minus mu squared. In this case, it's going to be 1.333 minus 1 squared. So this is the variance. And the standard deviation is going to be actually larger than this, because when you take the square root of this, it's of a number which is smaller than 1, its square root is going to be larger than that. All right, so this is how we solve this other example. Again, let me repeat, in order to find the variance of a variable, you need to find the expected value of two things, two functions. The expected value of the variable itself, and also the expected value of its squared random variable. And the difference between the squared expected value of the squared and the square of the expected value of the random variable is the variance, which is this. Okay, so what I was saying in English is this: the difference between the square of the expected value of the random variable and the expected value of the squared random variable. So it's like a riddle, right? I mean, lots of squares, expected values, so it may be confusing, but yeah, this is okay. The variance non-zero, a very good question. Question is, how could we find variance non-zero when we have a horizontal line? The horizontal line does not mean the variable itself is, the random variable is not variable. It's variable. It changes. It gets all the values between 0 and 2, right? It may take 1.2, 1.3, 1.5. So the random variable itself is variable, but its probability density function was constant. In that case, so if we go back to let me stop annotating my GIMP page. So if you look at this one, if you look at the PDF being constant does not mean that the variable itself does not vary. It varies, okay? So we can get, if you take, for example, 10 random samples from this distribution, you may get 0.2, 0.5, all of them equally likely. So it is variable. Here the PDF is constant. It doesn't mean that the random variable itself does not vary. The random variable varies between 0 and 2. We would get variance 0 in the case if we have a PDF that is like this. For example, if this is 1, this is 1, 2. If this is the PDF, a single point, okay, all the other parts is 0. Okay, so the PDF of a variable with 0 variance looks like this. A single, it's not a horizontal, no horizontal line actually. It's just a single point with a probability of 1. So the probability to get 1 is equal to 1. So it's defined like this. Fx is equal to 1 if x is equal to 1 and 0 elsewhere. Okay, if you look at this partially defined function, in this case, the variance will be 0. All right. Good question. So, yeah, we talked about this variance again, and now we are going to look at covariance, which is when we have two variables. And as I said, let me repeat that again. In this course, we're not going to talk about multivariate statistics, which contain many variables. We are going to usually look at most two variables. And in the case where we have two variables, the measure of their relationship, strength of their relationship, for example, if they are independent, that measure of their strength between their relationship is 0. Okay, for independent, yeah, is there a question? There was, I heard a sound. I thought there was a question, but yeah. But feel free to interrupt me if you have any questions. Okay. When we have two variables, when they're independent, the covariance between them is 0. But if for dependent variables, we still need how dependent they are. For example, if they are exactly, they're like always in sync, in parallel with everything. Their values are directly, for example, imagine one variable is x, the other variable is 3x. All right, three for one when one of them increases, the other also increases. Okay, x and 3x. Okay, there's a linear relationship between them, so they're really, really independent. And in that case, the variance between them is going to be very large. But there may be certain variables which may be dependent on them, but not so much as that linear relationship. For example, the height of a person and weight of the same person. Okay, height and weight are related somehow. If you're taller, you're bound to get a larger weight. But you may also be a thin person with, I mean, you may be 185 centimeters long, but you're still maybe 75 kilos if you're very thin. So there's a relationship between them, but this relationship is not one-to-one. Okay, so because there are large people and thin people, so that's the relationship is not directly one-to-one. So, but they are still dependent on each other. So the to measure the strength of the relationship between two different random variables, if they're not independent, if they're independent, it will be zero. What we compute is going to be zero. What we define is called covariance. Covariance between two random variables is defined as the multiplication of their individual differences from their means. Okay, so if you look at this, this is very similar to the single variance itself. If this was the same thing, if this was x and this was x, we would get variance, right? I mean, x minus mu x squared. It's the two of the same thing. If we just drop this square and the other thing becomes a different variable, how is it different from correlation? We are going to come to that. I haven't defined correlation yet. Correlation is the normalized version of covariance, actually. Let me directly answer your question. So correlation is the same as covariance, but it's normalized between -1 and 1. Covariance, as you can see, is not necessarily between -1 and 1. If you multiply, because if you, for example, multiply these values, they become large. Covariance can be arbitrarily large. Covariance can be arbitrarily large. Correlation, which is also called correlation coefficient, between correlation between two variables, is the normalized version of that, which is right here. Let me stop annotate first. So this is the correlation. If you divide the covariance you find by the square root of their multiplication of individual variances, you will get a unitless ratio, which is always going to be between -1 and 1. The correlation is also represented by this Greek letter rho, lowercase rho, and you're going, this is always be -1 and 1. It's a good way to standardize, to normalize these things, because, as I said, a large when you talk about covariance, when you say that, okay, the covariance between these two variables is 3, okay, it doesn't make any sense. Is 3 large? What is their individual variances? If their individual variances is like 100 each, okay, the variance of x is 100, the variance of y is also 100. 3 is going to be a small covariance, right? I mean, so this is exactly what correlation coefficient is doing. 3 by itself does not mean anything. You have to standardize it by dividing it by the square root of their individual variances. So in order to find correlation coefficient, we find the variances. We also compute the covariance by finding that. In order to compute covariance, again, implicitly we need to find the individual expected values. So finding ex and ey is always done, whether you're finding individual variances or covariance. And the difference between the individual, it's very similar to, you don't need to memorize these actually, it's very similar to what we had, right? Just in the case of individual variance, right? It was expected value of x squared minus mu x, mu x. So if you just want to make one of them mu y, you're going to get the multiplication of their individual expected values, the difference from that, from their expected value of their product, gives us the covariance. So if there are two independent variables, I told you that if there are two variables that are independent, the covariance is 0. This also tells me that if you want to find the expected value of a product of two independent variables, we had something in the example like, right, throwing of two dice. If somebody asks you their product, what is the expected value of their product, if these two are independent from each other, throwing one dice is independent from throwing the second dice, they are two independent things, you can actually compute, product expected value of the product will be equal to the product of the individual expected values. All right, so this is again for independent variables. We can do that, but covariance really measures, if you look at this, when it's changing from its mean. Now intuitively, let's try to understand what's going on. For example, if you just pick two random sample from our sample space and look at its x value and y value. Okay, for example, when we say height of a person and weight of the same person, we need to pick somebody and look at both variables on that same person. This x and y are not from two different individuals, from the same individual, but they are two different random variables. Now, for example, if this is the mean, the average of the weights of that population, this is the average of the heights of that population. So this basically measures, when you look at the weight, is it larger than the population weight? And for example, when it's being larger, if this is also, if that person height is also larger than the population height, we are going to multiply two positive things, which will result in another positive, right? Or if you find an individual and the weight of that person is smaller than the population mean, if that person's height is also smaller than the population mean, we are going to again multiply two negative numbers. This time it's also going to be positive. So if random variables, the two random variables for an object together are above the mean or below the mean, for example, what it means is that when one of them is increasing, the other is increasing too. When one of them is decreasing, the other is decreasing too. If we have such a thing, as you can see, it's going to contribute positively to the covariance. The covariance between them is going to be large. But if one of them is increasing, the other is decreasing, we are going to get negative values in this case, right? If, for example, if the weight is large, it's above the mean. On the other hand, the height is below the mean, we will get something negative. In independent variables, this relationship is totally random. When one of them is high, the other is low, the other is high, the other is also high. I mean, if there's always an inverse relationship between them, that doesn't mean, I mean, if we always get negative values from here, it means they are still dependent, right? I mean, there may be two variables, for example, like x and minus x, two variables which are totally dependent on each other. But when one of them is increasing, when x is increasing, minus x is decreasing. So the relationship between them is they're inversely correlated. In that case, it will be a very large negative number. And in the case of correlation coefficient, it will be very close to -1. Okay, so very dependent variables, if they're negatively dependent on each other, the correlation coefficient will be close to -1. And if they're positively correlated, it will be close to 1, their correlation coefficient. If it's close to 0, it means that we get positive contribution, negative contribution. They're just all over the place. There's no relationship between them. This one increases, the other one decreases. So this will happen, for example, if you just select random points on a 2D plane and look at their x and y coordinates. If you just uniformly select random points on a plane, can you say the x and y coordinates of these points are dependent? No. For some points, x coordinate will be large, y coordinate will be small. For some points, y coordinate will be large, x coordinate will be small. For some of them, both of them will be large, both of them will be small. So the x and y coordinates, if you pick random points on a 2D plane, they are not dependent on each other at all, okay? Because the Cartesian coordinate system, these are two independent coordinate axes from each other. X and y coordinates do not matter actually. But if you pick these points from a line, if you have a line that is drawn on this 2D plane and you pick the xy coordinates from the line, then that's something different. The correlation between them is going to be 1, all right? Because or -1, depending on the slope of the. Does the case? Yeah, I think that's the case. Yeah, depending on the slope of the line, whether it's negative or positive, you either get 1 or -1 in terms of x and y coordinates. The covariance. So how do we get it simplified like that? Again, actually, we can just take it out, and by using linearity of expectation, we are going to find this. So let's try to actually derive that formula, which is what is the expected value of x minus mu x multiplied by y minus mu y, right? Whatever I have here, whatever function here, I can just write it by using mathematics. I have to multiply everything by each other. So it's x times y. So it's going to be x times y minus x times mu y, right? Then I have minus y times mu x, and I have plus mu x mu y. Okay, so did I do this multiplication correctly? So x times y, it's here. X times minus mu y, x times minus mu y is here. Then minus mu x times y, minus mu x times y is here. Then two minuses plus mu x mu y. So it's this, okay? Now take a look at, let's try to, now since these are summation of individual items, because of linearity of expectation, this is simply equal to expected value of exy minus the expected value of x times mu y. Actually, I can directly take this mu y out because it's a constant. So mu y times the expected value of x, all right? I did it for this one. And minus mu x times expected value of y, and mu x plus mu y. Now, we don't know what this is. This is going to remain like this. What is this? What is ex? It's equal to mu x, right? Expected value of x, I can write expected value of x is mu x. So I have mu x minus mu y. What is expected value of y? It's mu y, right? So I have 2 mu x mu y, and I have 1 plus mu x mu y, which is just minus mu x mu y. So this, in other words, this is exy minus mu x mu y, which is the same formula you got on the slide. Okay, so this is how we simplified it, by using linearity of expectation. I hope it's clear. All right. So this is covariance, and correlation is just again defined to standardize everything to between -1 and 1. We multiply. So the covariance is again some multiplication of 2 units. For example, its unit will be if you take if you look at this, is it something going to be unitless? Let's see. So this is kilogram times centimeters, for example. It's kilogram centimeters minus kilogram centimeters. So its unit is kilogram centimeters. So here we have some unit kilogram centimeters, and these are kilogram squared, centimeter squared. Take the square root, again it's kilogram centimeters. So correlation is something unitless. We are multiplying something or which with whatever the unit of x and whatever unit of y is, covariance is those two units multiplied. The unit of covariance is those two units multiplied. And if we divide it again by the same kilogram, centimeter thing, or whatever the units they have, and the variance x squared, it's kilogram squared, and you take the square root, it's again kilogram. And this one is centimeter, so it's going to be something unitless, which is going to be, so you're normalizing however large those kilograms, you're normalizing it with the standard deviation, individual standard deviation multiplication of individual standard deviation. So you could also have written this as like it's covariance divided by standard deviation of x and standard deviation of y. It's the same formula, right? Covariance between x, y. So this one here, square root variance of x, is standard deviation of x. This is standard variation of y. So correlation coefficient could also be written like this. All right. And yeah, this is used a lot in, to analyze different features, whether they're related or not. Correlation coefficient is used. This rho is used to as a measure of independence relationship between two variables. Okay, so this was my last slides from week 2, set week 2. Okay, so if there are no questions, I'm going to now go to families of discrete distributions, in which we are going to see a number of different experiments, events, or different variables suitable for modeling different things. And it's really interesting. Most of real life phenomena is going to be able to modeled by one of these random variables or combinations of these random variables. So when we have these combinations, so we are going to see Bernoulli distribution, binomial distribution, geometric distribution, negative binomial, and Poisson. I think these are the families of distributions, and their names may be intimidating at first. Oh, binomial, negative binomial, but they're really simple things, really. Okay, so we are going to see how simple they are, and we are going to talk about the expected values of these distributions, the variances of these distributions, as we have learned before. The easiest, the simplest this discrete random variable is a random variable which gets just two values. A single random variable which gets just 0 and 1, nothing more. That's called a Bernoulli distribution, and such an experiment is sometimes called a Bernoulli trial. And in a Bernoulli trial, you make an experiment, and the result of this experiment is binary. For example, you can use a Bernoulli trial to create a random graph. This is, for example, imagine you want to create a random friendship graph between students in this department. You want to create a graph structure in which you're going to create your graph like this. The set of vertices are going to be the students in this department. And in order to determine whether there's an edge between two students, in other words, whether two students are friends or not, you, for example, may make a Bernoulli trial saying that with probability 0.2, they will be friends. With probability 0.8, they will not be friends. So a Bernoulli trial, unlike the a coin toss, for example, is also a Bernoulli trial where we have the probability of heads 0.5 and probability of tails 0.5. Sometimes we denote the values in Bernoulli trial 0 and 1 as success and failure. For example, in this case of friendship graph, is they're friends or not friends, or whether to put an edge here is successful or unsuccessful. So you can actually make Bernoulli trials between all pairs of students and create a graph which has some density, or it will have an average degree of some expected. I mean, the average degree of the graph is going to be 0.2. So I mean, the average, not the average degree, it's 0.2 times the number of students in your graph. Okay, so the average degree will be 0.2 times number of students for every one of them. But this is we can actually compute it by making use of, that's actually that average degree is going to be another random variable, which is going to be the binomial distribution. Because between two specific students, you make a Bernoulli trial, and that is a single experiment. There's an edge or not. If I said two specific students. Now, if you just fix one of those students and do the same experiment between all the other students in the department, you're making n. If the number of students is n, you will be making n Bernoulli trials. And in how many of those trials you will succeed, you will have edge. It's the expected number is going to be n times the individual success probability, right? It's going to be, you would expect 0.2 times n, like let's give some values to n. If there are 100 students in the department, you would expect the average degree to be 20 for in this graph. Okay. By the way, such a random graph is also called Erdős-Rényi graph, in which the single edges are determined by a Bernoulli trial. So in maybe social network analysis or graph analysis, these random graph generation is used a lot. And this is the simplest random graph that you can have. Okay, so a Bernoulli trial, as I said, it's very simple. We have a single experiment with a single outcome, 0 or 1. So it's going to be its probability, a mass function is going to look something like this. Okay, I have a 0 here, I have a 1 here, I will have some probability here, I will have some probability here, and whatever this is, for example, this is 0.2, this is 0.8, they will add up to 1, and this is just the probability that this mass function is going to contain only 2 values. Any random variable with 2 values could be modeled with this. You could have, for example, not necessarily 0 and 1. You could have a trial in which the values you can get is either 1 or 100. Okay, you get 10 or 100, for example. Again, it's between 2 values. Okay, if you have this and the other takes the values this. If you have any binary 2 values a variable can get, can be modeled by a Bernoulli distribution. Now, in the case of, in general, Bernoulli trials are not equally likely outcomes. It's going to be equally likely if the success probability is 0.5. In general, F1 is not equal to F0, so they're not equally likely. So if somebody gives us the probability to obtain 1, so we imagine we have a Bernoulli variable which takes values of 0 and 1 only. If the probability of 1 is p, what is the expected value and the variance of this Bernoulli variable? So what we need to do is this. So if the expected value of x, by the way, in all these distributions, they will have certain parameters to describe that specific distribution. Therefore, with that parameter being as a variable, we call these distributions family of distributions. Family of Bernoulli distributions are distributions where the random variable gets 2 values. If your random variable gets 2 values only, we call it's a member of the family, Bernoulli family of distributions. What fixes the distribution in that family is to give that parameter some value. For example, when I say p is equal to 0.2, I'm referring to a specific distribution, specific Bernoulli distribution. But when I'm talking in general and talking it as a variable, like the success rate is p, it's a family of distributions. Now, so in Bernoulli distributions, when the success rate, and if we get values of the probability to get 1 is p, and the probability to get 0 will be 1 minus p, what is the expected value here? The expected value, as you know, we computed as 0 times the probability of to obtain 0, 1 minus p, plus 1 times the probability to obtain p, which is to obtain 1, which is p, it's equal to p. Okay, so the expected value is simply p. So, which means that if you're whatever your success rate is, in the long run, you would expect that many of our. I mean, this is basically the center of gravity of that distribution. The expected value of the Bernoulli trial is p. Now let's figure out the variance. In order to compute variance, I need to compute the expected value of x squared, right? How do you compute the expected value of x squared? 0 squared 1 minus p plus 1 squared p. The expected value of x squared also turns out to be p, right? Now, if it's p, am I going to get 0 for the variance? No, right? The variance is expected, the variance is expected value of x squared minus this squared, which is p minus p squared. So this is the variance of a Bernoulli trial, p minus p squared. This is not necessarily 0, right? And is it going to be a negative number? P minus p squared, variance should always be positive, right? This seems like a negative number. Is it negative? No, right? It's less than 1, exactly. In the case of this 0.2, we will find it as you can see, this is going to be 0.2 minus 0.04. It's going to be positive, not negative. Perfect. So since the probabilities are always between 0 and 1, so p is defined as it's the parameter of the Bernoulli distribution, and it's the probability, so it's always between 0 and 1. So this minus p squared is always going to be smaller than p. And you can also actually write it like this. You can write it as p times 1 minus p. So that 1 minus p, right? This is also p minus p squared, p times 1 minus p. And you can even write it, what is 1 minus p? This is the non-success probability, sometimes written as q. Failure probability. If the success probability is p, failure probability, which is 1 minus p, is sometimes written as q. So its variance is going to be p times q. So an interesting thing about the Bernoulli trial that I want to mention is that the variance is going to be largest for a certain value of p. So when, for example, we have p is equal to 0.01 and q is equal to 0.99, it means that you get failures most of the time. Or if p is equal to, for example, 0.99 and q is equal to 0.01, you get successes most of the time. So when something happens most of the time, it means that it's not that variable. So the variance in this case, in these extreme cases, also for example, in the most extreme case, when p is equal to 1 and q is equal to 0, the variance is 0, right? You don't get any variance. You always get successes. You always get failures. Variance is going to be largest when p is equal to 0.5, right? This is expected. So when the failure and success rates, success have the same probabilities, you would get the highest variance, which is going to be 0.25. So if you have Bernoulli trials, the largest variance you're going to get is going to be 0.25. So, which is 0.5 times 0.5. So it's for all the other values of, you can actually draw a plot of p times q when p is changing between 0 and 1. It's, I think, going to be something like this. It's going to be a graph which is like this as we go from 0 to 1. Okay, when p goes from 0 to 1, this is p times q. So the graph of p times q when p changes between 0 and 1 is going to be something like this, and the maximum value is going to be attained at 0.25 here. Okay, so this is how the variance is changing. We are going to use this, we are going to see this 0.5 later when we talk about in hypothesis testing and in normal distribution, when we are going to assume the worst case, for example. In that case, if we don't know anything about the distribution, we are going to assume the worst case, and this will be our worst case, 0.25, the largest variance we can have for these Bernoulli trials. Okay, so some of the things may not make sense right now, the statements, but just know that this in Bernoulli trial, this is the simplest case with just one parameter. Bernoulli distributions have one parameter, success rate, and its variance is p times q, its expected value is p, and that's it. And by the way, the expected value and variances of all these random variables, we are going to give them also to you. You don't need to memorize them. In the midterm exam, in the cheat sheet, they're going to be provided to you. The first page, we are going to give all the expected value and variances of these families of distributions will be given to you. So do not try to memorize them. All right, as I said, if you have missed what I had stated in the beginning of this class, I'm going to have a block of 1.5 hours of lecture today, and I'm going to leave early, so we're not going to have our break. Okay, I'm going to continue for about another half an hour, and we're going to call it a day after that. When we have non-zero one binary outcomes, for example, what if the two possible outcomes are 5 and 9? Is the expected value still 0.3? So what is success and failure here? So they're not 5 and 9. Maybe 9 is success, 5 is failure. Is the expected value 0. And the p here is 0.7 for this. Is it the expected value? Is the expected value going to be 0.7? It doesn't make sense, right? It should be somewhere between 5 and 9. If we take two of these values, 5 and 9, the expected value should be between 5 and 9. So in order to compute the expected value, what we need to do is multiply 9 with 0.7 and multiply 5 with 0.3 and add them up. That will be so the weighted average of these two variables is going to be 1.5 plus 6.3, 7.8. Is it 7.8? So we have 1.5, 6.3, it's 7.8. So the expected value in this case is going to be 7.8, which is closer to 9. And it makes sense because obtaining a 9 has a higher probability. Yeah, it's 7.8, thank you. Also, if you want to compute the variance, there's another thing. So if you look at this, 5 and 9, so actually this is the more clever solution. Instead of trying to figure it out nice like this, you can have your random variable x defined to be as the Bernoulli trial multiplied by 4 and shifted 5 units. Okay, so if something gets 0 and 1 values, when it's 0, you get a 5. When it's 1, you get a 9. Okay, so this is the Bernoulli variable, our Bernoulli variable. And the variable that we have just defined here is a linear combination. It's a linear function of our Bernoulli trial. Since it's a linear formula, then we can use linearity of the expectation to write it like this. And since the expected value of this Bernoulli trial is 0.7, all you need to do is 4 times 0.7, add 5 to that, you get the same 7.8. Okay, so this linearity of expectation we use it a lot in these when there's a random variable which looks like a linear combination of another random variable. Now, actually, binomial distribution is such a distribution. Binomial distribution is like Bernoulli trials done a number of times. So it has two parameters. A Bernoulli trial had just a single parameter p. A binomial distribution has two parameters, n and p. Okay, n is the number of Bernoulli trials. P is the uniform static success rate, success probability of each of those Bernoulli trials. In other words, for example, if you have an unfair coin, imagine you have an unfair coin in which the probability of getting heads is 0.3, and probability to get a tail is 0.7. Okay, now if you toss the coin 50 times, what is the expected number of heads you're going to get? It's going to be simply 50 times 0.3. So which is going to be like the expected value of a single Bernoulli trial. In this case, is going to be 0.3. That's my success rate. The expected number of heads, if I throw the coin only once, is 0.3. But if you toss the coin 50 times, if you perform this Bernoulli trial 50 times, what is the expected number of total successes? This is what this binomial distribution is. And in that case, it's going to be the expected value of the other case. So this is Bernoulli, and the expected value of the binomial variable is going to be this 0.3 times 50, which is 15. You would expect 15 heads when you toss the coin 50 times. All right, if we have an unfair coin with the probability of head being 0.3. So this is binomial. So, and binomial on the other, binomial is just actually a summation of Bernoulli trials. Okay, so it's because the total number of successes in m Bernoulli trials is just again a linear combination of n independent Bernoulli trials. So you may also write it as expected value of this plus expected value of that. And since we have p, all of them are p, and we have n of them, it will then be n times p. So the expected value of the binomial variable is going to be that. By the way, I can read this one. So, here is the probability mass function of that. What is the probability to obtain, for example, so this was the expected value that we talked about. We can also talk about things like in Bernoulli trials, what is the probability we are going to obtain 10 heads in 50 trials? When we toss the coin 50 times, what is the probability that x is equal to 10 could be obtained by this probability? All the ways you could choose 10 from 50 multiplied by p to the power 10. 10 of them will be successes, okay, out of this trial, and 40 of them will be failures. Like the probability to get 10 of them success and 40 of them failure is this probability, p to the power raised. So it's 50 coin tosses, 40 of them failure, 10 of them success. So it's this probability. But the number of ways you can observe this is like for a specific single outcome. But there are many outcomes in which you can choose 10 heads out of those 50. And this is this 50 choose 10 is your is that many heads you can distribute in 50 trials. And this is what this one is saying. Okay, total number of trials and the number of successes you're looking for. P to the power, this was the success probability to the power x, q to the power n minus x. So this may be difficult to actually sometimes compute, and therefore this is the case where this is the place where I'm going to show you probability distribution tables, how we refer to them, which are given as cumulative distribution tables at the end of the book. We are going to take a look at an exercise for that. But since it's a probability mass function, this is a discrete probability, we can also compute probabilities of individual values of x can take. And just like the expected value and variance, we have of the variance is just multiplied by n. By the way, I have when I came here, I've just forget about certain properties of variances. We talked about linearity of expectation, but when some variable is a linear combination of other variables, how its variance changes, I haven't talked about that. You don't need to memorize these formulas, but there is a table at the end of this here. Let me show you expectation and variance. So this was we have talked about linearity of expected values. So it's very simple. But when we come to variance and standard deviation, the linearity of expectation, actually you can find those formulas by yourself, but it may be a little bit complicated actually. So look at this table, the properties of variances and covariances. We are going to give you this table again in the exam. You don't need to worry about memorizing it. But what is interesting is that so look at this in particular cases. When you have a linear combination of a variable like this, ax plus b, and its variance is not just a times, as you can see, it's not a times variance of x plus b, not like expected value, because variance is like a difference of square with the other thing. So therefore, when we're talking about variances which are squared and we have a linear combination of different variables, what you need to do is square that coefficient in front of x and multiply it by the individual variance of x. And since b is a constant number with no variance, it just disappears. Okay, in the expected value, b stayed in the expected value. But when we're talking about variance, since we're taking the differences here, constant values, they just disappear in when we try to when we compute the variance of some linear combination using the variance of individual random variables. And in the case of two random variables, ax and cy like this, it's basically whatever coefficient we have in front of them, they're multiplied together, and the covariance it becomes a multiplication. It becomes the covariance, and when they're independent, when we have two independent variables, the covariance is 0, as you can see here. And the variance of x plus y in this case, for independent random variables, it's their individual variances summed up. Okay, so therefore, when we were talking about the variance of a Bernoulli trial here, binomial here, it was the many independent Bernoulli trials with individual variances as pq, pq, pq. So we are adding n different p times q's. That's why it's n times pq. The PMF is like this. Let me try to describe it again. So for example, imagine, let me try to describe it on a simpler example, like five coin tosses. Okay, so when we have 5 coin tosses, and when the probability of heads is 0.3, and when somebody asks what is the probability that I will obtain 3 heads, okay, so when we have 5 coin tosses, when the number of the binomial distribution, when n is equal to 5, the number of successes and failures, the different values this discrete random variable can take, changes between 0 to 5, right? I mean, since these are all non-zero probabilities, probability of success, probability of failure is 0.9, it's possible to get all tails. In 5 coin tosses, I can get all tails. I can get all heads. These are all possible. And there will be 2 to the 5, 32 different possible ways, possible outcomes in my sample space. Now, if I describes, so my random variable is the number of heads. Okay, so x is number of heads. What is the probability that number of heads is equal to 3? So what you should do is, first of all, if you look at a particular case, number of heads is equal to 3 and 2 tails. This is an outcome where I have 3 heads and 2 tails, right? What is the probability to observe this single outcome? The probability to observe this single outcome, if they were all equally likely in this case, would be just 1 over 32, right? But here in binomial distribution or in Bernoulli distributions in general, we don't have equally likely outcomes. So observing a t and observing an h, these are not 1 over 2 each because we don't have a fair coin. The outcomes are therefore not equally likely. So what is the likelihood to obtain, what is the likelihood of this specific outcome where I have first is head, the second is head, third is head, this one is tail, this one is tail? The probability is basically 0.3 times 0.3 times 0.3 and 0.7 and 0.7. Since these are each of these coin tosses are independent, the probability to obtain a head from the first is 0.3. That's a Bernoulli distribution. The probability to obtain a head in the second one is also 0.3. This one is also 0.3. This one is 0.7, 0.7. So the probability of the specific outcome is this. In other words, the probability to obtain all 5 tails is 0.7 to the power 5, while the probability to obtain all heads is 0.3 to the power 5. As you can see, they're not equal. Now, when we talk about, so this is the 0.333 and 2 sevenths. So this is a specific outcome where I have 3 heads. Is it the only outcome that I have 3 heads? No. I can have, for example, tail, tail, head, 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 head. I can have tail, head, tail, head, head. Okay? Now, if you look at all of these, tail, tail, head, head, tail, head, tail, head, head, they all have this exact same probability because 3 heads, 2 tails. 3 heads, 2 tails, what does it mean? P to the power 3, Q to the power 2. Okay, so this probability is the probability of all those individual outcomes. How many of those individual outcomes do I have? How many different ways you can choose 3 out of 5? So it's basically 5 choose 3. This refers to the knowledge that we give you as a reading assignment, which was in the combinatorics phase. Yeah, exactly. It's going to be 5 choose 3 is going to be 5 factorial divided by 3 factorial times 5 minus 3 factorial, which is 2 factorial. So it's exactly that. It's exactly that many times. So the probability, therefore, is going to be this 5 choose 2 multiplied by these individual probabilities. And this formula is exactly that. Okay, so yeah, thank you for asking the questions. These are really important, and it also helps you to review what we have seen earlier in combinatorics as well. So yeah, binomial distribution, and this variance comes from the fact that it's a summation of individual Bernoulli trials, x1 plus x2 plus x3 plus x4, each of them with the same variance pq. And since all these Bernoulli trials are independent, I have n of them, the variance also becomes this. But in general, if, let me write it here, if you have something like this, if in general, if you have a random variable and a multiplication of that random variable like this, and this is the variance of this is going to be a squared times the individual variance. Okay? But we don't have a multiplication. The binomial distribution is not a product of n Bernoulli trials. It's a summation of, because it's defined as the total number of successes. When you say total number of successes, it becomes a summation. All right. If you define it's interesting. You could have another distribution in which you could have individual Bernoulli trials, and the variable that you define may be a product of those individual Bernoulli trials. Imagine I don't know in real life what it means semantically to multiply those. I mean, summing up those have an intuitive meaning, total number of successes. Like multiplying them, I don't know what it will mean in English, but maybe in some domain you may have individual Bernoulli trials like x1 x2. They may be individual Bernoulli trials, and you may define a random variable as their summation. But in that case, it's not going to be, if it's a product, it's not going to be a times x. So that doesn't also make sense. It's going to be x to the power n. Okay, so if you define a random variable like this, x to the power n, that will be totally something else. But yeah. Oh, having 5 different tree heads in one trial at the same time. I don't know. That's it. 5 different tree heads. Yeah, it's difficult to comprehend, but yeah, it may be something like that. Yeah, but here, and this is I mean, if you have a random variable, which is like a multiplication with some constant number, the variance will be a squared, the individual variance. I just wanted to remind you this. This here is not related to that. It's a summation, but it may still be like this. Now, I'm going to show you an example. 3.16, and also maybe go ahead and take a look at some Octave Online functions. Sometimes this computing these combinations and taking the power very large number, I mean p to the power 20, q to the power 10, it may be a little bit cumbersome to compute all these probability mass functions for individual values. So for that, we refer to cumulative distribution function tables. At the end of the book, in the appendix table A2, let me go ahead and take a look at go to the end of the book, the appendix. Well, there are 2. Yeah, here's now part of it is distribution tables. Like there's 17 pages of distribution tables. So let's take a look at those distribution table. Look at this table, binomial A2, table A2. This one is the binomial distribution table. So the cumulative distribution function is written. Remember, the cumulative distribution is the cumulative probability, the probability that you obtain at least, you obtain 10 successes or less, for example, x successes or less. The probability that x is less than or equal to x is the cumulative distribution function. And for that, you need to sum up for all possible values of k from 0 to x, you need to compute this and sum them up. So it may be, as I said, difficult to compute this for large values of n and k especially. So tables like these are provided as a lookup table to compute certain probabilities. These days, actually, nobody uses these tables. These tables are a tradition from very old times, maybe in the early 20th century, late 19th century, we had these tables. These days, we can directly, maybe people were using this before computers, right, or before personal computers. But these days, we can actually query individual very probabilities, CDFs, directly by implementing this in MATLAB or in some other language. So how do we read this table? Let's see. It has, the table is provided for a family of binomial distributions. So there is a P here, there is an N. So the table is given for if the number of Bernoulli trials you have here in this binomial distribution, the table goes only all the way to 18, right? No, there's this, yeah, it's continued 18. So what is this? Y, yes, so it's actually there's 18, 20, and 25, and that's it, okay? If, for example, in your binomial distribution n is equal to 30, you will not find your probability in this table. So only for certain small values of n, this table can be used. And these are the probabilities that are given for particular success rates. The success rates are given for 20 of them, or in increments of 0.05, as you can see. If your success rate is 0.18, again, you are not going to find it here. You will not be able to use this table. So it's really it's limited, actually. Only for certain values of p and certain values of n, you can take a look at this table. And it will tell you, for example, if n is equal to 4 and p is equal to 0.5, for example, or let's go, for example, 0.6. Success probability 0.6. And the number of heads in 5 coin tosses. The probability to obtain 0 or less, no heads, is 0.01. The probability to obtain 4 or less heads in 5 coin tosses, when the success probability is 0.6, is equal to 0.922. What is the probability to obtain 5 or less heads, which is not written here in 5 coin tosses? It's 1, right? I mean, it's the final value. The largest we can get is 1. Exactly. So it was like another trick question. So as you can see, all the values here, 0, 1, 2, 3, 4 is not given because it's all 1. It's cumulative. The largest value it's going to attain is going to be 1. So by using this cumulative probability distribution, cumulative tables, we can actually also find individual probabilities. CDF is given. What if you require PMF? Since PMF is the individual differences, for example, what is the probability to get 3 heads in 5 coin tosses, again with success probability 0.6? Let me try to annotate here. Okay, so we are looking at here, and we have 5 coin tosses. The probability to get a single head is 0.6. If I ask you, what is the probability to obtain, what is this? Px is equal to 3. Okay, is it this? 0.663? No, this is actually exactly, it's going to be, we subtract this from here, because with the inclusion exclusion, it's like using the inclusion exclusion principle. Again, you can find intervals. For example, the probability x is equal to 3 is going to be the difference between the CDF, which is, I can write it in capital F3 minus F2. Oops, I just erased everything by clicking on some shortcut here. So F3 minus F2 is going to give me the probability to obtain exactly 3 heads. Okay, so this cumulative function, so it's already, that information is implicit here on this table. PMF is already here. Now, we can also use MATLAB to query, especially for things that are not on this table. Let me go Octave Online, octaveonline.net. So there's this function that we can use, and here, binomial CDF. We can give x and p. So let's try one of those. For example, binomial CDF 3, 5, 0.6. Oh, I think I need to package load statistics though. Package load statistics. All these are in the statistics package. Now let me run it again. Yeah, 0.663. So this is, can I zoom in on this? Yeah. Look at this. When I load after I load the package, I can, what is this? The CDF of 3, when we have n is equal to 5, success rate is 0.6. These are the 2 parameters that are given. You get this one. And if you look at 2, you get this. And by subtracting one from the other, you can get, oh there's also PDF, let's check that Binomial CDF 250.6. This is the probability to obtain exactly 3 heads. And we can actually, if there's a function for that, I think, Binomial PDF or PMF. Does it PMF? Let's see. 350.6. No, I think it's also, they use the same probability distribution, probability. Yeah, they get the same. It's not, it doesn't distinguish between continuous and discrete variables. So the probability density function in continuous case is also referred to as probability density function or probability distribution function. There's no such thing as probability distribution. So it's actually probability mass function for discrete cases, but it's also the function in MATLAB is referred to as PDF if you want to access the probability mass function for the binomial distribution. Okay, so and the good thing is that by using this we can query larger things. For example, what is the 17 in the case of 40 coin tosses and the success rate is 0.62. Look at this. This is something that is not in the table. 40 coin tosses, success rate is 0.62, not an increment of 0.05. This is not in the table. And what is the probability to obtain exactly 17 heads? If it's like this, oh, I use PMF again. So it's this. It's a small probability because the value is the discrete, but it's still a non-zero probability, as you can see. What is the probability to obtain 17 or less heads? Let's go to CDF. It is a larger number, but it's still a small number, okay? Because probably, yeah, since it's like 0.62, getting larger numbers is more likely. So getting a small number of heads has a small probability, 0.009. All right, so that's, if you look at example 3.16, and after that I'm going to stop today, and we are going to continue on Tuesday for the different distributions. But if you look at example 3.16, let's go to chapter 3 and 3.16. Example 3.2, or we have now in the family of distributions, we have covered most of chapter 3. Oh, and I went too far. No, we're actually 3.4 right here. If you look at 3.16, look at this. Its solution is very simple, actually. So as part of a business strategy, randomly selected 20 of new internet service subscribers receive a special promotion from the provider. A group of 10 neighbors signs for the service. What is the probability that at least 4 of them get special promotion? So we are trying 10 times. N is equal to 10 here. Success rate is 0.2. And we are looking for the probability that at least 4 of them. So we are not asked CDF directly. What is the probability that X is greater than or equal to 4? When I say at least 4 of them. In that case, this at least 4 of them will be equal to the complement. Sometimes we are going to be using this complement events when we are solving problems a lot. So you will also need to get used to this way of thinking things. The probability of obtaining 4 or more successes is equal to 1 minus. It's the negative event of what is the probability to obtain 3 or less successes. Okay, 3 or less successes is the complement event of obtaining 4 or more successes. So therefore, this one is the CDF that is in the table. 1 minus this F3 is going to give us this probability that we are looking for. Okay, so we can find this from the Bernoulli, or we can also find by using Octave Online. We can find this F3 like this. The Binomial CDF 3, 10 trials, and success rate is 0.2. Okay, As you can see, it gave you 0.8791. It's exactly the same thing in the book. So let's look at the other example. An exciting computer game is released. 60% of players complete all the levels. 30% of them will then buy an advanced version of the game. So only the people who are going to buy the advanced version of the game are 30% of that 60%. Among 15 users, which we know only 60% of that is going to complete all the levels, and out of that, 30% is going to buy the advanced version. So among 15 users, what is the expected number of people who will buy the advanced version? So the success probability in this case is going to be 0.6 times 0.3. In other words, the probability to buy the advanced version is the probability of completing all the levels and buying advanced, which can also be given as the conditional probability like this. So the probability to complete all the levels was given as 0.6, and if provided they complete the levels, so out of the people who complete all the levels, the ones that buy advanced versions are 30%. So it's actually this conditional probability that was given in the question to us in that sentence. So 0.18 is our success probability, 15 is n, so the expected value becomes 2.7. And when we ask what is the probability that at least 2 people are going to buy it, we can again compute it by 1 minus PMF of 1, which is the summation of these P0 and P1. Sorry, not PMF, CDF of. So this one here, the probability that we are asked, what is the probability that x is greater than 2 is actually equal to 1 minus CDF 1, right? 1, 0 is not included here in this one. And in that case, CDF of 1 is equal to PMF 0 plus PMF. So it's what is written here. Probability of 0 and probability of 1 is written here. If we add these two things, subtract it from 1. And here we don't need to look at the table because we can directly use the PMF function directly to compute these values. Because n choose 0 is 1, n choose 1 is n. So we can compute these combinator n choose 2, n choose 1, or n choose 0, n choose 1 easily. So they're put into this equation directly without even referring to the table. And at the end, we find ourselves this probability. So these two exercises was also introduce you to the way of thinking in the complement way. When we are asked the probability, sometimes we think complement events. We compute the probability of those complements and subtract those from 1 to find the desired probability. All right, so this concludes Bernoulli and binomial. We have seen two distributions. Similar, we are going to continue these and we are going to talk about geometric distribution, which is defined as the number of Bernoulli trials needed to get the first success. So that's interesting. Now, n is not given to us. You're asked to how many times, what is the expected number of trials until you get the first success? So this is a really interesting distribution, which can get values from 1 to infinity. I mean, if the failure probability is non-zero, failure probability is non-zero in most of the cases like that, the probability that you're going to keep trying until infinity, that probability is a non-zero probability actually. You will never get to 0 by multiplying, for example. If the failure rate is 0.1, 0.1 times 0.1 times 0.1 times, continue this all the way to infinity, you will maybe then reach 0, all right? So I mean, what I mean is that it's a non-zero probability. So therefore, this number, as it's defined, the number of Bernoulli trials needed to get the first success is a non-zero. I mean, it's a number between 1 and infinity. So we will talk about this. So I have to leave now. We are going to talk about this on Tuesday next week. I will stop recording now.